In this session, let's focus on understanding some of the statistical concepts and how they really are linked to the financial world, especially in terms of understanding the market returns. In general, when we talk about the statistical methods, we are more and more interested in a big, huge set of data, the analysis of that particular data, as well as inferences or conclusions from that data. That's the major objective when we are applying some kind of statistical concepts. And primarily when I am looking at the financial world, I may want to analyze the various returns, stock returns, bond returns, or probably I want to assess the prices, the stock prices, the commodity prices, or I may be interested in looking at the growth rates, different kinds of growth rates, or for that matter, any such kind of a financial data over a large period of time. I want to do some analysis, and based on that, I may want to derive some kind of conclusions from that data. Or I may be even interested in doing some kind of forecastings or predictions based on the observation of the large volume of data. So, this is where statistics is really helping me out, right? So, overall, when I look at the intention of understanding statistics for finance professionals, it is majorly to address this kind of an objective. So, any data that is presented, we are interested in understanding the various dimensions of that data, and probably should lead us to make some kind of inferences and conclusions, or even help me in doing some kind of forecastings once I have a look at that particular data. So with that in mind, the broad agenda for this session is, I would talk about initially the basic concepts relating to statistics. First of all, the different branches of statistics, or probably discussing about different types of measurement scales, etc. Then the next two subparts, I am focusing more and more on summarizing the data. One, using the frequency distribution, because one important thing what I wanted using statistics is a better presentation of the data. Once the data is presented well, the analysis and conclusion making becomes more easy. So the summarizations, one using a frequency distribution, or probably doing a graphical representation. Then we look at a few sections relating to the quantitative computations on the data. Right, I am looking at the quantitative computations on the data, where I talk about for a given data, how is it centered, which is called as a measures of central tendency, and how is it dispersed, how is my data deviating from the center or dispersed from the center, which are talking about the measures of dispersion. Is the pattern of my data more or less symmetrical, or is it lopsided or skewed towards one side? So that is something which we would try to understand. And finally, are the extreme outcomes, are they likely or not? So that is what we are trying to understand through the various mechanisms. And finally, we'll try to see some kind of investment related applications, where I really need to use either a geometric mean or an arithmetic mean, or what is that I am going to, and how can I decide what I can use in what kind of a context. So with that as a base, let's simply get started with the basic fundamental concepts of statistics. So whenever I initiate the basic fundamental concepts, I need to understand what statistics is all about. What do I mean by statistics? probably two major definitions come out. On one side, we say some data is statistics. Means I have collected the statistics regarding the population of this particular country, which is nothing but I have collected the data regarding the population of this particular country. So sometimes people use the word statistics to mean data, and in some cases, or in most of the cases, statistics means some methods or tools to derive or analyze the data and derive some kind of conclusions out of it. So, in general, the statistics as such got broken into two major dimensions. One is the descriptive statistics, where we talk about summarizing the data properly. So, some kind of representation, some kind of graphing, charts, summarizing of the data, wherein large sets of data, even if I have large data, I can very well summarize it or consolidate that data so that I can convert that data into useful information. The data is getting transformed into a useful information. So that is what is being taken care by the descriptive statistics. So either I summarize, I do basic computations on the data, all those are going as a part of my descriptive statistics. Whereas when I am talking about the inferential statistics, there is something else that is coming out, wherein my intention is to make some kind of conclusions from the data that the descriptive statistics has given me. I may have to make some kind of conclusions or forecasts or judgments about the data, where I take a small set of data and try to make conclusions about the large set, which actually involves mechanisms like sampling and hypothesis testing. Two major areas that drive this inferential statistics world, whereas the computations and all, they drive the descriptive statistics world. And the base for this entire inferential statistics is nothing but the theory of probability, which we'll be dealing slightly later. So it all starts off with doing some kind of calculations and basic summarizations using the descriptive statistics, and use the concept of probability theory and various probability distributions, which we would be covering in our later sessions. Probability theory and probability distributions get into the inferential statistics, where you take some samples and perform hypothesis testing on the data and try to reveal some kind of conclusions about it. So this is the broad concept or framework in which the statistics would be operating. Now, another important dimension that I would like to get in is, we have been using the word sample. So I just want to differentiate between population versus sample. Whenever I talk about all the members of a group, I call it as population. Whereas if I am taking a subset of that particular group, again here it need not be people, it can be even the returns data, the prices data. If I am including almost all the data from the group, I am calling it as population. But if I am taking any subset of it, I am calling it as a sample. And any measure of this population, like if I am taking the mean of this population, or if I am taking the standard deviation, any measure or any kind of calculation that I am doing on this population, I call it as parameter. Whereas any kind of calculation I am doing on the subset, which is the sample, we call it as a sample statistic. Any calculation or any parameter that describes the population, I call it as parameter. Anything that describes the subset of the population, which is the sample, I call it as sample statistic. Right? Probably many a times we use the words like mean, standard deviation, range, etc. Those are all, if I am finding it on the entire population data, I call them as parameters, and if I find the same on the sample data, I call them as sample statistic. Sometimes, though the data is available regarding the entire population, but working on that entire data could be either pretty much expensive, or it may be time consuming. So it is really not advised to work on the entire data, even though the entire data is available. So that's where sampling and proper sampling methods are different kinds of concepts associated with the sampling are there, so that I can take a subset of the entire population in a judicial manner and based on that make my workout and basically provide conclusions regarding the entire population. In most of the inferential statistics world, we work only with the sample of the data, but we make conclusions relating to the population. So that's the beauty of using statistics in a decision making scenario. But the sample needs to be chosen in such a way that it's a good representation, or it has almost all the characteristics of the population in a large manner. That is one thing which needs to be looked at. There are different kinds of sampling methods which I would be dealing with in the later parts of the sessions. So that's one kind of an understanding that you need to develop between the sample as well as the population, and the parameter as well as the sample statistic, because majority of the times what we do is we try to estimate. In conclusion making, we try to estimate the population parameter. We try to estimate the population parameter using sample statistic. That's the key driver in this entire inferential statistics space, right? So we'll get into those things slightly at a later stage. Now the other important concept that I think that we all need to be comfortable with is the data. The data, what are the different scales in which we can look at the data, right? Generally we talk about the four major scales. One is a nominal scale, two is an ordinal. Either we can have the data in the form of an interval scale or even a ratio scale. So I see typically four different measurement scales for looking at the data. One, when I am looking at the nominal scale, probably it is the weakest, because this is purely a textual data or a categorical data. Right, the categorical data, I am assigning some quantification to the categorical data. Probably I am simply saying a categorical data something like 1 means male, 2 means female. I am assigning some kind of a quantification to the data. 1 means male, 2 means female, but there is no ranking to it. No ordering or no ranking. So it doesn't mean that 1 means 1 is greater than 2, or the items which are marked 1 are better than the items which are marked 2, or vice versa. There is no such kind of a ranking among the data items, among the categories. So such a kind of a scale is what I call as the nominal scale of data. But when I move slightly towards an ordinal scale, again here I am talking about sorting the data as well as ranking it. I'm sorting it as well as ranking it. So probably if I say 1 is high performing, 2 is medium performing or moderate performing, 3 is a low performing. So here the 1, 2, 3s, whatever I have given, there is a order to it, there is a ranking to it. Whereas here there is no such kind of a ranking. Here also I am doing the categorization of the data only, right? It's still a categorical data, a quantification being done to that categorical data, but the only difference is here there is some kind of a ranking. We are using numbers to identify different kinds of categories, but at the same time it is even talking about the order, the hierarchy in which each of the categories are ordered. 1, 2, 3 here means 1 is the best, 3 is the worst, or in some cases I may have a different way. 1 means the worst, 3 means the best, but whatever it is, as the number is increasing, we are seeing some kind of a change in the order. So those kind of data is what we call as ordinal data. But still, here this data does not tell me about the differences being equal. So the difference in the numbers need not be the same, like the difference between 1 and 2 as well as 2 and 3. Mathematically this difference is equal, but I'm not sure whether high performance to medium performance is same as the difference between the medium performance to low performance. So here the categorization of the data, only the ranking or only the categorization of the data is important, but the difference between the different ranks is not clearly communicated in the ordinal scale. But when I move my data towards, when I look at a data which is in an interval scale, it provides ranking just like in the ordinal scale. It also makes sure that the differences between the ranks are equal. Differences between each of the ranks, it ensures that the differences between them are pretty much equal. Probably even the survey questions, if I am designing, 1 means highly satisfied, 2 means moderately satisfied, 3 means okay, 4 means dissatisfied, 5 means highly dissatisfied. Generally, though I may not be though I can directly say that it is an ordinal data because it is doing some kind of a ranking from highly satisfied to highly dissatisfied. But generally what the survey people will be doing is they assume that the gaps between each of them is more or less the same. The gap between highly dissatisfied to dissatisfied is same as the gap between highly satisfied to satisfied. So if the assumption of that is if the same, then we call that kind of a data as an interval data. Otherwise I have to treat it as an ordinal data itself. But the biggest problem here is 0 here does not mean absolute nothing. What I meant by that is probably the best example I should consider in this case is the temperature. When I talk about 10 degrees C versus 11 degrees C, the difference is 1 degree. Similarly, 25 degrees C to 26 degrees C, even this is 1 degree. So the difference in the temperature between this and this is the same. But when I say 0 degrees C, it doesn't mean that there is no temperature. It only talks about as the freezing point of water. It's not an absolute 0. It doesn't mean that there is no temperature. Because when I convert the same 0 degrees C into Fahrenheit scale, it is giving me something else, 32. It's not giving me an absolute 0 in a different unit of measurement. So those kind of data where the differences are pretty much fine. So when I have to look at it as 11 degrees C, probably I'll call it as 10 degrees C plus 1 degree C. But I cannot say 11 degrees C is 1.1 times or 10% more than the 10 degrees C. Probably this kind of a multiplicative relationship does not come in. So ratio multiplication cannot be applied to the interval scale data, because an absolute zero does not mean the complete absence. It's not a true zero. It's not a natural zero. Whereas when I talk about ratio scale of data, probably it incorporates all of them. So it incorporates all the characteristics of the interval scale, but at the same time it is having a true zero. Let's say heights, height of a person, weight of a person, money. Zero money means no money. Zero height means no height. Zero weight means weightless. So zero is an absolute zero, right? So ratio scales, we are able to compute the multiplicative relationships also. Probably when I am saying height is 20 centimeters, probably I can say it is 10 plus 10, 10 centimeters plus 10 centimeters, or twice that of 10 centimeters. So both the multiplicative relation as well as the additive relationship can come out using the ratio scale of data. So we can apply wide range of statistical methods. Different kinds of statistical calculations can be applied on a ratio scale data, whereas there is a limitation in terms of application of those to a nominal scale or ordinal scale or even an interval scale data. So that's one more dimension. Coming to the financial world, probably if I just look at the credit ratings, they fall under the ordinal scale. Just to give you, credit ratings, they fall under the ordinal scale. Any kind of probably the dividends or years, maturity periods, lot of money related, they all fall under the ratio scale. But any kind of fund classifications, not the performance wise, just a fund classification based on the style, they all go as a part of the nominal, because there is no ranking or anything provided on the data. So this is another major thing that we really need to be comfortable with. Alright, now let's look at the next important aspect, wherein we'll start summarizations of the data. So I'll talk about summarization of the data first in a tabular kind of a format, wherein I will look at doing it using a frequency distribution. One of the simplest approaches to summarize the large volume of data that I have. So basically when we are creating a frequency distribution, it's a kind of a tabular approach. So I break the whole data into different intervals. I divide the whole data into different intervals and try to count the number of observations that are falling in each of the intervals. So a tabular display like this, where I am identifying the intervals and then trying to count the number of observations in each of these intervals, that is what we are calling as a frequency distribution. So large volumes of data, even if I have a huge data, I can identify the maximum and the minimum values of the data, and based on that I can divide the entire data into a finite limited number of intervals. So even if my data is very huge, or even if my data is having any kind of a measurement scale, nominal, ordinal, interval, or even ratio, any of the scales data can very well be summarized using the frequency distribution. Another important advantage. And coming to the financial application world, we look at we'll try to take up the rates of return, which is used almost by almost various investment managers, portfolio managers, analysts. Almost every group of people typically use the return rates. So based on that, I would like to do some kind of analysis on the rates of return. So I want to do some kind of frequency analysis of that data. So I've taken a small data set. Right, I have taken a small data set which talks about the monthly returns of Sensex, or the monthly values of Sensex right from January 1991 till October 2014. So this is the data I am carrying. The index values right from January 1991 to October 2014. Now I would like to do an analysis of the returns, and we know the return here, the return I am taking as the holding period return, which is nothing but the index value or the price at period t minus price at period t minus 1, plus in case there is any dividend that is declared during the period t divided by the price at t minus 1. So that is what we call as the return, holding period return during the time t. So the same logic here, without any kind of a dividend or intermediate cash flow in this case, I can take the return as this return, this value minus this value divided by the previous period's value. So here I am getting that the return is around 24%, and probably the same way I can extend, except for the first month in February there was a return of 24%, in July at 28%, whereas in May 1992 I am seeing a minus 22, in March 1992 I am seeing a plus 42. So these are the different kinds of returns that I have looked at. Now this returns probably how much period, how many observations are there? Almost 286 observations are there associated with the returns, right now I have 286 observations associated with the return. Now corresponding to this entire 286 observations, I want to create a frequency distribution. Now if I am looking at that, so the major thing, if at all I have to look at creating a frequency distribution, is if I have to do it, I need to know what is the minimum value in the data. So once I sort it in ascending or descending, I can easily identify it, but using a spreadsheet probably I can very well rely on finding out the minimum value. So there is a minus 23.89%. that is the typical minimum value that is there in my data. Then I want to find out what is the maximum value in the data. So in this, the maximum value is coming out close to 42%. So 42% is working out as the maximum value, and based on that I can identify the range of my data. Range goes as the maximum value minus the minimum value. So the range is working out to some 65.89%. So I am identifying the range. Now I am also interested now in identifying how many intervals are there to depict that particular data. So depending on the range, it's better that I choose the interval, and to a large extent it is expected that the intervals I can plan out. The interval can very well be planned out as a integer rather than a decimal. So if I'm looking at 10 intervals, right, or probably I should plan out, if not the interval, I should plan out the range of the interval as an integer. So probably I can very well think the width of the interval. Either I can choose an integer number of intervals, which can very well be done, but at the same time it would be better that if I choose the width of the interval as an integer. Width of the interval I choose as an integer. So probably if I say I need number of intervals, let's say I plan it to be around 10. This I can choose. How many intervals do I require? Let's say I am choosing the number of intervals to be 10. So based on that I can find the width of the interval. So I could really look at the width of the interval as this divided by 10. Doesn't matter, 0.065% is the typical width of the interval. So probably I could have very well rounded it up, right? I could very well round it up to a nearest 2 digit, or probably I can continue with it. There is no hard and fast rule. So if I am looking at now the width of each of the intervals, now I will try to create the intervals. Right, now I will try to create the interval. The minimum value is something which I am taking here. The interval maximum value is what I am taking here. So to start with, for the first one, I am starting from here, and the next thing is going as this value plus the width. Right, so this is what up to minus 17.3 is my interval here. Whereas here I am taking again that the minimum is minus 17.3, the maximum is going as minus 10.7. Like this, if I am typically going a bit down, I am getting it from minus 10, minus 4. So if I am looking at the number of intervals, I am actually getting. So I really need to see how many intervals. Up to 42 I need to create the interval. So this is where I am getting, if I am looking at the total number of intervals here, I am getting 10 intervals because the maximum is up to 42. Now what I can very well do is, now that I know that this is the interval, this is the maximum, this is the minimum. So I can very well write it. I can very well write the things as minus 23.89% less than or equal to the observations less than minus 17.3%. So this is the way I can very well plan out all my observations. Right, and once I have created something like this, now that I have got my intervals, so these are the intervals that are created. Now I can very well find out of my data how many are falling into each of these intervals. So that is what I call as frequency. So I'll use a function called countifs, which talks about within this particular range, I want to see the values which are less than or equal to minus 23.89% and the values which are here, okay, minus 23.89, so which are greater than minus 23.89 and which are less than or equal to minus 17.3. So I want to find out of that whole set of observations, how many of them are between minus 23.8789 to minus 17.3. So there are 3 such observations. Minus 17.3 to minus 10.7, there are 15 such observations, and so on. So if I am trying to summarize or sum up the total frequencies, it is coming to 283. Why is this coming out to 283? Greater than minus 23.89. So I have to go with a greater than or equal to. So here I'll go with a greater than or equal to something, but this side I'll take it as less than only. So to achieve this, probably I require a little bit on the higher side. So that's the reason, because if I'm taking the minimum and the maximum exactly equal to this, the intervals are getting slightly, I need to get both the minimum value as well as the maximum value into my observation. So if I'm going ahead with that kind of a process, it is clear that there are 284, or probably here greater than or equal to this much and less than or equal to this. So it's better that the width of the interval, I increase it a little bit to accommodate all the classes quite comfortably. So so that the minimum can be included as well as the maximum can be included. In general, what we do is greater than or equal to the minimum value, and only we look at less than the maximum value. So even if I do that, here it comes out to be 285 observations, and this is how I am able to summarize that entire set of values. So it is as good as saying minus 23.89% less than or equal to the number of observations, each of the observation less than minus 17.29%. So here it becomes minus 17.29% less than or equal to the observations less than minus 10.69%. So this is how I see the less than here, or I see the less than here, I see the equal to coming into the next group. So this is a better way of organizing the data and finally computing the frequency. So these are my intervals, minus 23.89 to minus 17.29 and so on. These are my different intervals. Each observation falls only into one of these intervals. No observation can fall into two intervals, because here only up to less than minus 10.69 comes, but if 10.69 comes, it falls here. So even there is no problem. Right, even if a value observation is minus 10.69, it will fall here only, not here, which means each observation will fall only into one single interval. And when I am looking at the total number of intervals, they should contain the entire data. That is where I was verifying. I required 285 data points, but when one or two were getting lesser, I had to rework in terms of adjusting the size of the interval so that all of them can be accommodated quite comfortably. So this is what is an assessment of the frequency, or sometimes that same frequency people call it as absolute frequency, because we are trying to just count the total number of observations, and based on the counts I am just putting the numbers there. So there is no kind of overlap. It's a unique kind of entry that goes into each one. Now how many intervals do I need to select? Though there are some kind of guidelines running, but I generally suggest probably having 7 to 10 on an average is a decent number of intervals. But sometimes it's always better to look at the data and based on that see the appropriate number of intervals, because if I use more number of intervals, right, if I am using more number of intervals, the number of observations in each interval may not exist many, which may result in so many blanks in terms of frequencies. But at the same time, that may result in too much of a detail, too much of detail going up. Whereas on the other side, if I have a very few intervals, right, if I am using very few, then the summarizing is too much. Heavy summarizing is happening. Heavy summarizing is happening on the data, and probably the patterns of the data and all are completely lost because not too much of details going into it. So we have to be very much careful. Look at the range. Look at how many zeros are coming up if I am dividing it into 10 intervals or 5 intervals or 3 intervals, and based on that plan out the appropriate number of intervals. Once I have computed the frequency, we also compute what we call as relative frequency. Relative frequency is nothing but the frequency of each of the observation, the frequency of each of the intervals divided by the total frequency. So that is what we are calling as relative frequency, and I can establish in percentage terms. So probably here it is saying 34.04% of the observations are lying between -4% to 2.5%. So almost in 34% of the total months, or probably 97 months out of 285 months, the monthly return has been between -4% to +2%. And a few only are there, and between 2 and 9%, almost 85%, that's next in the list. So a relative frequency is directly providing me which of the intervals are very highly valued, which of them are having a very few number of occurrences. Probably I could see between 28 to 35 or between 35 to 42% in 1 month. They are very rare occurrences, which means probably they can very well be treated as some extreme kind of months as well in my data. And similarly, the same compared to the relative frequency, we also talk about cumulative relative frequency, wherein we are simply adding up. When I am talking about cumulative, it's accumulating as we move from the first to the last interval. So for the first interval, I take the same as the frequency, but from the second interval onwards, I try to add the relative frequency of the second interval to the cumulative up to that second interval. So overall, what is happening is once I reach to the last, I'll get the 100% value, which also means if I'm so basically all I am doing is I am adding the frequency of that particular class to the cumulative frequency up to the previous class. So here it is telling me, it is giving me a kind of an indication that probably 22.11% of the observations, 22.11 percentage of times, the Sensex has fallen by 4.09% or more, or the return on Sensex was minus 4.09% or less in 22.1% of the cases, or probably in 96.14% of cases, 96.14% of months, Sensex return is less than 15.7%. So either it goes into a loss are only in 3.86 percentage of the cases, Sensex has given a monthly return of greater than or equal to 15.7%. All these kinds of summarizations can very well be brought out once I am looking at the cumulative relative frequency. So this kind of a thing is giving me the one kind of an information where most of the observations are lying, what is the interval, and at the same time how is the distribution. Probably if I am seeing from here there is a gradual fall up to here, from here also there is a gradual fall, but probably towards the extremes I am seeing almost no observations. So here this will also tell me the shape of the distribution. Probably when I talk about the graphical part, I could clearly see the moment I plot a graph, I could clearly understand whether the distribution is more and more even towards both the sides, or is it more skewed towards one direction. All such kind of things can very well come out, because probably analysis of large and small outcomes, either this side or this side, the analysis of large and small outcomes are the worst and the best kind of outcomes. Probably we need to understand the characteristics of them so that they could be presented, or they could be visualized in a much better manner. So at the same time I could even visualize how many of the observations are positive, how many of the observations are negative. I can derive any such kind of analysis in my summarizations. Probably I could have made sure in such a way that I have got a minus and a up to 0 as one interval and 0 2 as some other intervals, or probably I could have counted how many of them are greater than 0. So probably if I am taking the positive kind of observations, I could have counted in this entire data how many of them are positive. What I could have simply got is 162 observations out of the total are positive. Means on an average around 56.84% of the months there was a positive returns on Sensex, and remaining 43.16% of the times they are negative returns on the negative monthly returns on Sensex. So even this kind of a quick summarization can very well be done. So this is what I can typically look at as a frequency table. I would see the intervals, and corresponding to each of the interval I am looking at the frequency, the relative frequency and cumulative relative frequency. So this entire thing presented in a tabular format is what we call as the frequency distribution representation. Alright. Now that we have understood the creation of frequency distribution, I am looking at the graphical presentation of the data. So as a part of the graphical presentation, I will look at three major graphs here. The same data I will look at from the frequency distribution. How can I convert it into a histogram? How can I convert the same into a frequency polygon? And how do I plot the cumulative frequency kind of cumulative relative frequency kind of a distribution? So these three graphical representations let's try out. So whenever probably we all agree to the fact that when I represent the data visually, the characteristics can be understood quite comfortably. I can look at the shape of the data. Is it symmetrical? Is it skewed to some side? And once I look at the shape, I can even visualize what kind of probability distribution I can associate to that kind of a data. Just by visually looking at the shape, I can see what kind of probability distribution is more apt for this kind of a data. So from all those perspectives, the plotting of histogram or a polygon or cumulative relative frequency distribution will be of a very good help for us. So whenever I talk about a histogram, it's just a graphical equivalent of a frequency distribution, right? While frequency distribution is a tabular form, the histogram is more like a graphical form. And probably if I am creating a frequency histogram, which again, the simple way I can work it out is, I'll take the different intervals. For each of these different intervals, I'm looking at the frequencies. So I'll take this interval, I'll take the frequency corresponding to each of these intervals, and I'll simply plot a column chart. That is what we call as a bar chart. I take the frequency interval, even in a simpler way, if I have to go ahead, for each of the frequencies, I'll plot a simple column chart. Alright. So this column chart, in technical words, we also call it as a bar chart. So I'll plot a bar chart with the frequencies, and probably in Excel I can even go with taking the x-axis labels to be something like this, and I can do this in such a way that I can reduce the gap, because in our data we don't have a gap, in our intervals we don't have a gap, so even in the histogram I should not see any gap. So this is the kind, I've reduced the gap using an Excel spreadsheet, and this is the kind of a shape that I have typically got from the histogram. So this is what I call as a histogram, and probably even these things I can make it a little bit more better. Instead of positioning the axis not in between the tick marks, I'll put it on the tick marks. What I could now see is between minus 23.89 to minus 17.89, this is the kind of a frequency. So I could very well talk about minus 23.89 to minus 17.29, this is the frequency. Minus 17.29 to minus 10.69, this is the frequency. So one way I could see is minus 4.09 to minus 2.5, this is having the highest frequency. Minus 2.5 to plus 9.1, this is having the next highest frequency, and so on. So this is what is giving me a decent picture in terms of how the frequency is positioned for different class intervals. So this is telling me that the shape of this particular frequency distribution is more from this particular perspective. So this is what we are calling as the histogram. Now the next kind of a graph that I am looking in this particular scenario is the frequency polygon, which is another representation of the frequency distribution. And when I am looking at a frequency polygon, I will take the midpoints of each of the class intervals. So I'll compute from this data, I'll compute the midpoints for each of the class intervals. I will compute the midpoints. What is the way I am looking at? I am simply taking the average of the minimum and the maximum value of the interval. So these are the midpoints. Now what I am doing is, I am taking the midpoints on the x-axis and I am taking the frequencies on the y-axis. So for different frequencies and for different frequencies, I am plotting this kind of a graph. So if I look at it, a simple line chart wherein I am looking at the frequencies, not this. For the frequencies, I am plotting a simple line chart. The frequencies, I am plotting a line chart, and this is what is the cumulative. This is what is the frequency polygon in my case. So all I am taking is the midpoints are taken on the x-axis. So here as a scale, what I'll do is I'll take the midpoints on the x-axis and the corresponding plots on the y, and I just try to close the figure before that and after that. So this is a better representation, and this is what I am calling as the frequency polygon. This is what is a representation of a frequency polygon, wherein I am taking the frequencies on the x-axis, the midpoints on the x-axis, and I am plotting the frequencies on the y-axis. Otherwise, I am calling it as a frequency polygon. So this is one more kind of a graphical representation. This is one more graphical representation that is coming for my data. And one more important graphical representation that is coming out for us is a cumulative frequency distribution is one more graph that we are primarily looking at, wherein I am taking the cumulative frequencies. But before I go, some of the important aspects that can come with respect to the frequency polygon is it adds more and more continuity, because there is a line that is joining the various points. So some kind of a continuity to the distribution is coming up, and that is one advantage that we are going to derive. Once I go with a cumulative relative frequency distribution, all I can look at is, I'll do a plot. I'll take a line chart again. I'll take a line chart, a fresh one. In that fresh line chart, I'm going to plot cumulative relative frequency of the data. Cumulative relative frequency, wherein I'm trying to select this part. This is my cumulative relative frequency. Now I am trying to take the cumulative relative frequency on the y-axis, and I am also taking the intervals on the x-axis. So I'll take the minimum values of the intervals on the x-axis, and that is what is giving me some such kind of a curve. I see this is what I call as the cumulative relative frequency curve, and what we are majorly observing in this cumulative relative frequency is I am able to see what percentage of the observations lie below a particular criteria, probably below 0. Okay, if this is my 2.5, let's say this is 0. If I want to know how many values are lying below 0, I can very well try to plot it. Again, I can very well try to point it at this particular point and say these many observations are showing a value below 0 and these many above 0. So what we could typically see is towards the very extreme, I am seeing that the curve is more flattening, either on the higher side or on the lower side. But somewhere in the middle, I am seeing that the curve is more and more steepening. So the slope of this generally is much more in the middle, and as we move towards extreme right as well as extreme left, we see that the slope is almost flattening out. So some kind of a quick observation on the pattern of the distribution can very well be made out using this cumulative relative frequency curve as well. In some cases, that same curve is also called as an Ogive curve. So some people call it as an Ogive curve, Ogive curve, whatever it is. And the other way we can plot it as a cumulative relative frequency kind of a curve. So these are the three important frequency distribution representations or graphical representation of a data summary, which can really help us in visualizing the pattern of the data and the underlying distribution that could be associated with our data. All right. So now that we are done with the representation of the data in a tabular and a graphical format, now we move slowly towards the understanding of some quantitative calculations with respect to data. So the quantitative calculations, the first of them, we will be looking at the measures of central tendency, which is nothing but how the data is centered. Right, so that's one thing. So we are trying to understand different kinds of characteristics of data using the quantitative calculations, and an important item out of that is the measures of central tendency, where we talk about where is the center of the data. Right, we can calculate that much easily, and majority of times we see that in a lot of applications, different kinds of measures of central tendency are being used. So, first of them, we talk about arithmetic mean, or sometimes in plain words we call it as average. Then we also talk about median, mode. Then we'll also start looking at a few other measures like weighted mean. Then we'll talk about geometric mean. And finally we will bring in harmonic mean. So these are different kinds of measures of central tendency that we are going to look at. So when I start off with arithmetic mean, the most widely used one, especially it's a representative number. When I am looking at so many data points, it is typically a representative number, which is generally a representation of the middle of the data. So we know how we compute it. We sum up all the observations and we divide it by the total number of observations. And if I do that for the entire population, I call it as a population mean. And population mean generally represented by the symbol mu. And it is one single number only because I am taking the entire population. So it's a one single number because it takes the entire population. Whereas on the other side, if I do the same computation on a sample, I call it as the sample mean. Generally I represent the sample mean with x bar. And it could have different values depending on the subset of the population that has been chosen, right? So this is typically just to remind you, the population related calculation is called as a parameter, whereas the samples related calculation is called as a statistic, right? And The notations we need to be comfortable with. Mu, whenever we see mu, it's an indication of a population mean. Whenever I am seeing x bar, it's an indication of a sample mean. And in general, we can compute the means for two kinds of data, either a cross-sectional data or a time series data. When I say cross-sectional data, different entities at a same point in time. So today at same point in time. So today I am looking at the different entities, let's say the heights of 30 people. 30 different people at the same point in time. If I am trying to take the data and do some computation, we call that kind of a data as a cross-sectional data. Whereas when I say time series data, it's for one entity across time. So probably I am looking at the profits of one company over the last 20 years and I am trying to find the average. Or I am looking at the age of the height of the person for the last 20 years and I am trying to look at some computations on that. So those kind of data are typically called as time series data. Whereas if I am taking the data of different entities at the same point in time, then I am calling it as cross-sectional data. And I can compute the mean both for cross-sectional as well as the time series data also. Now, let's try to compute the mean for the data and then see what all we can infer from it. So let me use the data which we have used for the graphical purposes as well. So if I say this is the data I want to look at, let me say what is the arithmetic mean that is coming up. I am summing up all the numbers and dividing by the total. So I'll take it, I'll use directly the formula called average, which is coming out to 0.01. But the way I could have got it is I do the summation of all these numbers and I count the total number of numbers here, number of observations. So arithmetic mean could have very well been the total sum of numbers divided by the total count of numbers, coming out to the same calculation. So here, when I got this 0.015, right, now when I get this arithmetic mean is 0.01503, it need not be any one of those values, right? It may be, it may not be. So it need not be any of those observations. It could be in the middle of any of two observations. So it's just a representation of the characteristic of the data. So probably one major measure that can be used to compare two different data points. Probably if I have got, if I have taken the data of Sensex, let's say the arithmetic mean came out like this. But if I take similarly the data relating to Nifty or probably the S&P or any other index, I can compute the mean of that and try to see whether the arithmetic mean, the mean returns are higher for Sensex or some other kind of index. Such kind of comparisons can be made quite comfortably. So there are so many observations which are above the mean. So because this is 0.015, probably if I convert it into percentage, it's somewhere around 1.5%. So there are so many observations which are above the mean and there are so many observations which are below the mean. So because there are observations which are above and below the mean, that is what we are associating it to a deviation. We'll talk about the deviation slightly later, but the ones which are above the mean and below the mean, this is what we are calling as deviations. And the good thing is, if I sum up all the deviations as such, sum of deviations from the mean, it is always equal to 0. Just let's try it out. I would like to find the deviation of each of the individual observations from the mean. Deviation. So I'll subtract this minus the mean. Right? Deviation of each of the individual observations from the mean, and I try to sum up all the deviations. Sum of deviations from mean. Just see what is that we are going to get. The sum of deviations from the mean is almost 0. 10 to the power of minus 16. So almost a 0 kind of a number is what is coming up. So that is what is one thing which we may have to keep in mind. The deviation from the mean, if I take it as it is and sum up, it is going to be 0. And very important as we move along in our finance understanding, individual deviations from the mean are very important, because we use those deviations as a measure of risk in the data. And a lot of other concepts which we are going to deal slightly later, the variance, the standard deviation, the skewness, the kurtosis, all of them are based on the same concept of deviation from the mean itself. Now, looking at the good things about this mean, the mean uses all these data points, right? It does not omit any one of them. The size, the magnitude of all these data points are being used very heavily, because it adds all of them and divides by the total. Now, because of that, there is even a possibility of a drawback. Let's say one extreme value can pull the mean very much on the higher side or on the lower side. So probably here, if I say instead of 0.97%, let's say I'm taking it as 100%. Just one extreme observation, let's say, has come out. What is happening is, what could very well happen is, your arithmetic mean could typically get, or probably if I take it 1000%, I should not change the deviation, I should change the mean. So instead of 2.48, let's say it is 100%, right, which is the return in a particular year. Let's say it's 100%. What I could see is the arithmetic mean suddenly has gone from 1.5% to 1.85%. So that is what is a very serious problem. Even instead of 100, let's say if I make it minus 100%, suddenly I see that the arithmetic mean has fallen to 1.14%. So this is what will create a problem with the arithmetic mean. If my data is having some extremely large or extremely small values, my mean gets suddenly shifted towards the right or towards the left. So what happens because of that is, the question comes up, how well it represents the center. How well does it represent the center? So that is where the mean has the drawback, right? The extreme values, the outliers, or is it really an error in the recording of the data? We really need to understand that. But But in general, mean is the most widely used measure of central tendency because of easy to work out mathematically as well. Now, the next important measure of central tendency that we are going to look at is the median. So, median does not do any kind of a calculation. It is the middle value of the data, provided you arrange the data in either the ascending order or in the descending order. So, if there are odd number of items in your sample, odd number of data in sample, you will have only one middle point. So n plus 1 by 2th element is the median. But if there are even number of observations, then what we typically see is n and n plus 2 by 2. N by 2 and n plus 2 by 2th elements, both of them will be taken, and again a mean of these two elements will be taken, and that is what we call as the median. So slightly complicated depending on the number of elements in the sample, whether it is odd or even. We see that the median calculation formula will typically differ, and median is generally called as the middlemost element. And what we see is, in case of a median, the good thing is equal number of observations will lie above the median and equal number of observations will lie below the median. So median is something that exactly divides the data into two halves. One half will be above the median, the other will be below the median. Right? Whether there is even number of observations or odd number of observations. The major advantage is it is not getting that badly impacted with the extreme values or outliers. Right? Even if I look at the computation here I need not arrange the data and pull out. I have a direct formula, but just to understand it, let's say I am taking the median of the returns. Okay, I am getting 0.012, fair enough. But the same logic, instead of 2.48 here, if I had taken 100, my median did not change in any way. Mean got directly to 1.85, but the median is still at the same 1.2. Means even if there was an extreme value, even if from 100, let's say I am making it to 200, mean is changing drastically, but the median is not getting impacted. So that is what is one advantage. Median is not that much affected because of extreme values. But the biggest drawback is, while mean was able to use all the values in the calculation, median does not use the values at all. No computation on the values happens. It directly picks only the middle element, and it is not bothered about any other elements which are surrounding it. So that's one more major drawback. It's only based on the ranking, and it's not considering each and every observation, and at the same time it has a slight complex calculation, because depending on whether the sample is odd or even, I'm changing the mechanism of computation of the median. So that's one reason it's not that easy to compute, whereas mean is something which is straightforward and easy to compute. Right? Now, the third important tool that I am looking at as a measure of central tendency is the mode, where we talk about most frequently occurring value. Most frequently occurring value in a distribution. So there could be a possibility for any distribution that there is no mode, means all the values are coming only once. There is no one single value which is occurring many number of times. There could be a unimodal where only one value is coming up maximum number of times. There could be bimodal, two values are coming maximum number of times, or even multimodal, multiple values coming maximum number of times. So any of them can be very much possible. And for the returns kind of a data here, where almost every value comes only once, because any possibility could be there because of the precision, there is a very good chance, if I am looking at the mode, there is a good chance that mode may not be present because no value is repeated more than once in the entire data. Even when I am looking at computation of the mode from this returns data, what I could see is there could not be even a single instance where one single value got repeated exactly the same. So for these kind of data, it's always possible that the mode may not be there. And whenever I'm sometimes, but we can look at the interval. Mode for an interval can be looked at, and in this case, probably when I'm looking at the mode for the interval, here I could quite comfortably make out that this is the mode. Right, when I'm looking at this being the interval, I could very well look at the interval that is coming with the maximum frequency could be the model interval. So between this number to this number represents the model interval for me. So that is what is a model interval, and whichever is the highest bar in the histogram, that interval can be called as the model interval. And another good thing with respect to mode is this is the only measure of central tendency which can be applicable even to the nominal data. Whereas all the others, mean and median, they are more and more applicable to the ratio scale data. Probably I can very well apply the mode even to the nominal, because whichever one comes with the highest frequency, that is what we call as the mode. Now, a few more apart from mean, median, mode. I also will look at the weighted mean. See, when we looked at a typical mean, right, when I looked at the typical mean or the average, we added up all the numbers. Probably if I had x1, x2, x3, so on, xn, we added up all of them and we divided it by n, which is as good as saying I have given a 1 by n weightage to each of the numbers. So when the weightage that is given to each of the numbers is uniform, we call it as a plain average. But when the weightage that is given to each one of them differs, that is what we call as a weighted mean. So typically used heavily in portfolio returns kind of examples, because my weightage of investment could be different in each of them. So I may be investing out of my total proportion, I may be investing some W1 in the first one, W2 in the first one, W3 in this third one. And let's say the W1 has given me a return of R1, the second one has given me a return of R2, and the third one has given me a return of R3. So if I want to find out my overall return, it is nothing but the weighted mean that I am going to take. So W1, R1, W2, R2, depending on whatever I have, so I can very well look at WI, RI kind of a mechanism. And here my W's are the weights or the proportions in which I have invested in each of them, and RIs are the returns on each of those instruments. And it may so happen that all the weights should sum up to 1. W1 plus W2 plus W3. So because I am talking about the total proportion of investment, the summation of all these weights should be equal to 1. And okay, in the language of portfolios, we can even talk about some of these numbers could be negative also, or some of the weights could be positive. If they are positive, we say we are having a long position. We'll discuss this slightly later. Whenever we are having a positive value, we say we are having a long position. Whenever we are having a negative value, we say we are having a short position in that particular investment. And typically, when I look at the examples, the market index, the Sensex, the computation of the Sensex itself is a weighted mean. Because the way the Sensex is computed, let's say there are 30 stocks that are included in the Sensex. The weightage to each of the stock is taken as the market value of the stock which has been included, market value of the stock which has been included in the Sensex, divided by the sum of all market values of the stocks which are included. So if I say ICICI Bank is included as a part of the Sensex, then the market value of ICICI Bank divided by the market value of all the 30 companies which are included as a part of the Sensex. So that is the weightage that will be given to ICICI Bank as a part of the computation of the Sensex. So that is how market index, the Sensex, which we are using, the data that we are using right now, that itself is a weighted mean computation. So most of the times what may happen is this weighted mean I may compute it based on the past data. But this weighted mean could be computed even on the forward looking or a futuristic expected data. So when I am using the weightages based on the expected values of the future, the same weighted mean gets a new name called expected value. So weighted mean, when it translates into the futuristic numbers, it gets called as expected value, right? So this is something which we need to understand about the weighted mean. Then the next thing which I am trying to present is the definition of the geometric mean, wherein we talk about the average, where we talk about average rate of change over time. Generally with time series data, over the last 5 years, what is the rate of change? Or when I am looking at compounded growth over the 5-year period, we use the geometric mean. So whenever we are looking at a time series related average, we are using geometric mean. And in general, geometric mean is computed as the product. See, in an arithmetic mean, we are adding all the numbers and we are dividing by the count of them. Whereas in case of a geometric mean, we multiply all the numbers and we raise it to the power of 1 by count. That is how we compute the geometric mean. The nth root of x1, x2, x3, xn is what is the mechanism for computation of the geometric mean. But one small thing that we need to keep in mind here, one of the important restriction for computing the geometric mean quite effectively is all these numbers need to be positive. All the numbers that are inside the root, they need to be positive or at the max 0. But what happens is the typical returns related data which we had here, the returns related data, there were negative values as well to a very large extent. So because of that, I may not directly apply the geometric mean concept to my returns data directly, because there could be negative values. So the first thing is I will try to make them positive. The first work which I may have to do before I want to find out the geometric mean is I will make them positive by doing 1 plus returns. So I do simply just a 1 plus return. So instead of having the returns now as RIs, I am taking 1 plus RIs to start with. Now what is happening by doing that small exercise is 1 plus Ri. If I am doing 1 plus Ri's probably with a number format like this, there is no way I am getting a negative number. All the numbers are positive. So first of all, each observation I have converted even the negatives into a positive by doing a 1 plus Ri, because my worst case in returns could be minus 100%. I cannot fall below 100% in case of stock prices. So the worst case could be minus 100%, which itself is getting translated into translated for us let me change this data again. Okay. So the maximum itself is 100%, which itself when I do 1 plus Ri, it can become 0. It cannot become negative at all. So because of that reason, I'll first do 1 plus Ri, which is giving me this, and whatever the product I do, the product I'll compute for 1 plus Ri. Okay, I do the product, I compute the product for 1 plus Ri. I compute the products of all these 1 plus Ri's, and for finding out the geometric mean, I take this product to the power 1 by count. So which is giving me that this is the geometric mean of 1 plus R. But I want the geometric mean of R. So because I require the geometric mean of R and not 1 plus R, what I typically do is I subtract 1 from it. So this comes out as the geometric mean in my case, which is 1.16%, whereas the arithmetic mean was around 1.5%. I could have used directly the geometric mean formula itself. So geometric mean using the formula, there is a formula called geomean. So geomean of these numbers minus 1. So even directly this should give me the same kind of an approach, 1.16%. So here in case of returns, I am slightly modifying the concept of geometric mean, because the returns could be negative, whereas the computation of the geometric mean expects all the values and all the calculations to be all the values to be positive. I am converting those negatives into positives by doing a 1 plus Ri, and first I am taking the geometric mean of 1 plus Ri, and based on that again subtracting the 1 back to compute the geometric mean of Ri. And just as an observation, we have seen that the geometric mean is less than the arithmetic mean. And let me tell you, it's always less than or equal to arithmetic mean. The equality will happen only when all observations are the same. When all these values are exactly the same without any kind of a deviation, then the arithmetic mean will be equal to geometric mean. But even a slight variation in the data could result in geometric mean strictly lesser than the arithmetic mean only. So especially for multi-period investments, multiple period investments, if I'm looking at looking at growth over the multiple periods, annual growth over I have invested for 5 years and I'm looking at a compounded annual growth over the 5-year period, or profitability over a multi-period kind of a scenario, then geometric mean is much more handy compared to arithmetic mean. But if I am looking at a single period performance, then obviously the arithmetic mean is the most important factor to look at. So that's one of the prime reasons. There is a lot of application surrounding the geometric mean for us. And finally, one more thing that I'm going to look at as a part of the understanding of the measures of central tendency is the harmonic mean. Of course, there are a limited number of applications, but the way the harmonic mean gets computed is the reciprocal of the mean of the reciprocals. So what happens? First let me compute, and then we will try to if I look at the harmonic mean, I am directly using the formula first. The harmonic mean, if I take for this for this particular data, if I am taking the harmonic mean, I am taking the mean of each of the observations, the reciprocal. Is it not able to compute? Okay, let me take for 1 plus r's at least the harmonic mean of this. So this is the harmonic mean of this, whereas I subtract 1 again, I can get that this has the harmonic mean. But what has happened is, first I take the reciprocals of the data, 1 by x. First I take the reciprocals. So let's say if I am going with 1 plus r only, the reciprocals of 1 plus r. Right, first I take the reciprocals of this. So these are the reciprocals. Then I will look at the mean of the reciprocals. I'll look at the mean of the reciprocals. And I take the reciprocal again. Reciprocal of the mean, I'm taking 1 by this. So this comes out as my harmonic mean for 1 plus r. I can convert it into the harmonic mean of r by subtracting 1 from this. So overall the harmonic mean is working out as 0.82% here. The best kind of a scenario probably in the finance world where I talk about the harmonic mean is when I am talking about the dollar cost averaging. What is this? Let's say I am investing in a fund. Right? Let's say I am investing in a fund. Every month I want to invest 2,000 bucks into the fund, a fixed amount. Right? 2,000 bucks is something that I want to invest into the fund every month. If this number is different, then probably harmonic mean will not be used. But let's say I am using 2,000 every month. So in the first month, the price of the fund, the unit value of the fund was 25 bucks. So because of that, I was able to purchase 80 units of the fund. because I have spent 2000 bucks, $2,000, I am able to purchase 85 units. But in the second month, it so happened that the fund value has gone to 20, which means with the same 2000 I was able to purchase 180 units. Now if I want to find out the average price per unit, right, 25 units, when it was 25 I have purchased 80 units, and when it is 20 I have purchased 100 units. Now what is my average price? I cannot take the average of these two and say the average price is 22.5, right? So it's as good as saying, okay, my total investment is 4,000, total number of units is 180, so my average value is probably somewhere around this. My average value is somewhere around 22 point something. It is not 22.5, 22.22. So this is what is being obtained through the harmonic mean kind of a mechanism. Only these if this amount has been different, then harmonic mean cannot be used. Only when it is the same, I am going ahead with the usage of the harmonic mean. Otherwise, I may have to depend on the usage of the typical weighted mean itself for each of these cases. So these are the different kinds of measures of central tendency that become more and more applicable for us, or that are more and more useful for us in evaluating various investment decisions. All right. Now that we have looked at measures of central tendency, now we'll focus our attention towards other measures of location, which we generally call as quantiles. Why do we really need to look at them? See, sometimes not just the center, I also want to have some information about the location, or identifying a value, identifying one single value below which a specific percentage of my observations lie. Some kind of percentage of observations. What is that cutoff value below which 75% of the observations are lying? Or what is that cutoff value below which 90% of the observations are lying? So those kind where I am not, see, when I am talking about the median, it's that particular value below which 50% of the observations are going to lie, at or below which 50% of the observations are going to lie. Similarly, if I want not just 55%, what is that particular point below which 25% of the observations are going to lie, or 90% of the observations are going to lie? So that is where I am calling them as the other measures of location, or generally using the word as quantile. A quantile directly tells me the value at or below which that stated percentage of the observations are going to lie. So generally we use a few common words in terms of quantiles. When I say quartile, I am talking about dividing the data into quarters. So more to do with 25%, 50%, 75% kind of observations. Or I could talk about quintiles, very commonly used word, where the data is divided into five groups, 20%, 40%, 60, 80 and the last. Or probably we are talking about decile, where the data is split based on tenths, and percentile in terms of hundredths. So whenever in my data, if I am talking about I want 18th percentile, it means that 18%, I have to choose that particular value where 18% of the observations are below it. I want to choose that value in such a way that 18% of the observations lie below it. But when I say first quartile Q1, it is as good as saying 25% of the observations are below it, because it's as good as calling it as 25th percentile. First quartile is nothing but 25th percentile. 25% of the observations lie at or below it. Similarly, when I am talking about D3, third decile is nothing but 30th percentile. So 30% of the observations lie below it. So in general, if I want to find out that particular value in my data which represents the white percentile, all we are looking at is, if I am having n observations, n plus 1 times y by 100 is my white percentile. So when I want Q1 data, it is the 25th percentile. So what I'll write it is n plus 1 times 25 by 100. So n plus 1 by 4th data is my 25th percentile once I have ordered the data in the arranging or the ascending or the descending order. But now this could be an integer, this may not be an integer. If this is an integer, straightforward. So probably in our case, okay, just to understand, if I want the 30th percentile, or which is otherwise the third decile in this, what I can very well say, I arrange the data in the ascending order. So 285 data points are there, right? Because I have 285, my 30th observation will be 285 plus 1 times 30 by 100. So actually I require 85.8th observation. I don't need the 85th or I don't need the 86th. So in some cases this could be an integer, in some cases it could be a decimal. So if it is an integer, straightforward, I will get the smallest 86th value. So what typically comes out for me is, I will find out the 85th smallest first of all, 85th smallest value. So I will use a formula in this to typically identify in this the 85th smallest value. Okay, so this was my 85th smallest value in that data, and probably I'll also find the 86th smallest, which will be within the same data. I'm looking at the 86th smallest. So this was it. Now I will use a mechanism called interpolation. Interpolation is the mechanism that I am using because I want 85.8th observation. I will take the gap between the 85th and 86th. Whatever is the gap that I have got between the 85th and the 86th observation, I take the 0.8 times that gap and I will add it up to the 85th observation. So according to me, my 30th percentile going with interpolation is the 85th smallest value plus, I am taking the gap between the 86th and 85th. That gap I am multiplying it with 0.8 because I want not the 86th but I want only the 85.8. So somewhere middle between, somewhere in between 85 and 86, but 0.8, 80% away from 85 and only 20% away from 86. So that's the reason I'm taking 85 plus 0.8 of it, which is giving me minus 0.024. That is what I call as the 30th percentile in my data. So probably I could even directly use the percentile as a formula. So in this particular data, let's say I want the 30th percentile. Okay, there is something else going on. So the simpler way to compute the 30th percentile for me is find L, which is n plus 1 times y by 100. Based on that, compute what is the observation that we are typically required to get your 30th percentile, and based on that apply it to the data and finally get the smallest observations and 85th observation, 86th observation, and based on that get your 85.8th observation. So that's a typical way we get into the computation of the different quantiles. In general, what we see is these quantiles are used very heavily in the investment practice, especially when we are developing the performance evaluations of the portfolios. We say that this is in the top 5 percentile, or we say that these portfolios are in the bottom decile, or probably we talk about these stocks are in the first quartile, whereas these stocks are in the last quartile. So I want to compare between the stocks of the first quartile and the last quartile. Or probably we want to do an evaluation between the value stocks and the growth stocks. So most of the times the value stocks, when I am looking at their price as a percentage of as a proportion of their earnings, they may be having at a very low values, which means they could be in the bottom decile when I look at their P by E kind of number. Whereas when I look at the growth stocks, they may be very much on the higher side with respect to their P by E, which means they could be in the higher decile, whereas this could be in the lower decile. So breaking the data into the quantiles and deciles actually enhances the interpretation, and probably even the comparisons between the data groups can be done quite comfortably. So that's where the usage of these different quantiles, especially quartiles, percentiles, deciles, comes in more and more handy, right? So that's about the other measures of location. Now we will slowly move towards the next set of observations or next set of calculations, which we typically classify as the different measures of dispersion in the data. All right. So as a part of the measures of dispersion, what we can simply say is, let's say from an investment perspective, we have computed the measures of central tendency quite effectively. But to understand an investment completely, along with the mean, I also need to know how my data is deviating from the mean, how much of dispersion is around the mean. Because mean is typically addressing the concept of return in the investment terminology, whereas the dispersion, any measure of dispersion, is actually indicating the amount of risk that is pertaining to that investment. And only when I understand these two things, I am able to interpret the data much better. So there are different measures of dispersion, just like measures of central tendency. We can talk about the usage of range, We'll talk about mean absolute deviation, or we'll use the very common forms of dispersion, which are the variance and standard deviation. Right? So, in some cases, apart from this, even we can talk about some kind of deviations with respect to benchmarks also. So, different kinds of dispersions can be typically looked at. So, getting started with the first of them, let's say the range. We simply easiest to measure kind of stuff. We look at it as the maximum value minus the minimum value of the observations. So that is what we are calling as a range. We have computed it earlier also in our data set, but going back to our data set, if I want to find out the range, I am taking just the maximum value of my observations minus the minimum value of my observations. So that is what is coming out as the range. But here the drawback is it uses only two values in my data. It does not look at all the values in the data. It looks just at the maximum value as well as the minimum value, and all other values are typically ignored. So if my maximum value and the minimum value are some extremes, probably it gives me a completely different interpretation, which may not be a representation of the shape of the data at all. So from that dimension, very rarely range is being used in the investment practice. But now, what else if it is not the range? So that's where I am looking at the mean absolute deviation. Now I want to have that kind of a measure which considers almost all the observations, not just the highest and the lowest. So earlier when I looked at taking the deviations of all the observations from the mean, deviation of all observations from mean, what I have seen is the sum of the deviation was always 0. So because the positives and the negatives cancel out each other. So I need to have a measure which addresses the problem of the negative deviations cancelling out the positive ones. So that is where the mean absolute deviation had made an initial move. What the mean absolute deviation has done is we don't take the deviation directly, we take the absolute deviations. Instead of taking the direct deviation, we take the absolute deviation from the mean. So we'll even if it is negative, negative will be taken as positive. That's the only difference. So I'll take the absolute deviation, whatever the deviation I have computed earlier, I'll take the absolute of it, means I'll ignore the negative value altogether. So you see here it was a minus 5.8%, but that became a 5.8% here. So that is what is my first step. I'll take the absolute of the deviations and I'll take the average of those. So when I say mean absolute deviation, first I am taking the absolute of the deviations of the mean, and after that I am simply taking the average of them. So in this case it is coming out that my mean absolute deviation is around 6.31%. That is how we compute the mean absolute deviation. So it is using all the observations, but the biggest problem is I have to compute mean mathematical absolute values, and mathematically it has a few problems in terms of linking all the statistical properties. So that's one of the prime reasons I may not be able to use the mean absolute deviation in practice. But yes, nevertheless it is much better than the range. So that's where I can go ahead in terms of looking at the value corresponding to the mean absolute deviation. Then What about the next? That is where we talk about population variance and the population standard deviation. So these are the ones which are widely used in the investment related applications. Even they focus on the deviation of each of the observations from the mean. Even if it is with population or if it is for sample, they focus on each of the observations from the mean. Whereas your mean absolute deviation was focusing on the absolute of these deviations, the variance focuses on the square of the deviations. Even that is to eliminate the negative deviations only. So we look at the square of the deviations around the mean. So instead of taking absolute deviation, let's say I take squared deviation. So it's as good as saying whatever the deviation that I have got, I'll take the square of the deviations from the mean and I'll take the average of that. So when I'm looking at variance, especially population variance, let me use the word population variance here because we'll change it slightly. So wherein I'm taking the average of the squared deviations from the mean. So this is what I'm calling as population variance, and when I take the positive square root of it, I call it as population standard deviation. So I take the square root of this population variance, I get the population standard deviation. So in this case, the standard deviation comes out to 8.4%. So when I am defining the variance, I am simply saying the average of the squared deviations from the mean, and standard deviation is going as the positive square root of the variance. And typically from a symbols perspective, when I talk about the population variance, I talk about sigma square. So simply it is like I am taking each of the observation, subtracting the population mean from it, squaring it, then summing it over all the n, and finally dividing by n. So this is what is the definition of the population variance. And so which means initially I have to find the population mean, and only once I have the population mean I can find the square of the deviations from the mean. But this is in a squared units. My data is in some units, but when I am looking at the population variance, because I have squared it, the units of that resultant variance is the squared units. So I want a measure that comes back to the units which are similar to my data. So that is where I want to, because I have squared it, I want something to come back to my original units, which means I want to take the square root so that I can return to the original units. So that is what is being addressed by the standard deviation. Standard deviation is nothing but it's a square root of the variance. So the unit for the standard deviation is same as the unit of the observations, or so that means it's more easy to relate standard deviation for interpretation compared to the use of variance, which is expressed in squared terms. But to compute the standard deviation, obviously I have to compute the variance. So directly the square root of the variance is what is giving me the standard deviation as well. So because these two are associated with the population, so population variance as well as population standard deviation, we call them as parameters. But if I am computing the same for samples, we call them as statistics. But in majority of the cases, what will happen is getting the whole population, getting all the observations as we have discussed earlier, is either too expensive or too much time consuming. So given going with that particular fact, we may be restricted always to a samples only. So if I am going ahead with the sample, I will find out the sample mean only, which is x bar, which I cannot talk as mu, and I have to go with the sample variance only, which is slightly different from the population variance. First, the notation. I will not represent it as sigma squared, I will represent it as s squared. Okay, each individual observation I subtract from the sample mean, square the deviations, sum them up, but the only thing is I will not divide it by the total number of observations, I will divide it by the total number of observations minus 1. I will not divide, so I cannot directly use the average, because I cannot divide it by the total number of observations, but I am dividing it by the total number of observations minus 1. So here when I am looking at the sample variance, for this I have to divide, first of all I need to add up, right, because in case of population variance I have taken a plain average, but here I have to add up. So I'll say sum of the squared deviations. First of all I'll take the sum of the squared deviations, which comes out to be this, and in case of computing sample variance I'll divide this sum not by the total number of observations, but I'll divide it by total number of observations minus 1. So the sample variance comes out to be slightly higher, and in a way if I am looking at sample standard deviation, again I'll go with the square root of the sample variance to end up with the sample standard deviation. Probably if I look at the sample standard deviation, in this case it is slightly 8.43%, whereas the population standard deviation is 8.41%. What is the reason? See, mathematically it has been proved, going beyond the proof, mathematically it has been proved that this particular value is an unbiased estimator of the population variance. We'll discuss about this word slightly later. But if I have to use a samples value for estimating the population value, we need to have an unbiased estimator. And what has been found out is the sample variance, which is denoted by this formula rather than this, has been a much more unbiased estimator for population variance compared to using this. So because of that reason, the statistical properties are very heavily improved when I am using n-1 in the denominator compared to usage of n. So this equation is an unbiased estimator of the population variance, and that's the reason we use that. And the other way of talking about the same is n-1 actually is called as the degrees of freedom. See, because I am going with a sample, the simple way for us to understand is, see, I am having so much of data, x1, x2, so on, xn, right? Now, let's say I have computed the sample mean, right? I have got the sample mean x bar. Now, once I have the sample mean, there are only n-1 independent deviations from it. If I am trying to find out the deviations of each of them from the mean, if I find, let's say xn-1, so the xn minus x bar I don't need to find, I can derive it, because if x1, x2, x3, xn have given me x bar, probably x1 to xn minus 1, they could change in whatever way they can. But obviously xn cannot change in its own way. It's an adjusting number to generate x bar. So which means this number, one of the observations, is not free for a change because it has to generate x bar as the mean. So from that perspective, there are only n minus 1 independent observation, which means I would be dividing the sum of the squared deviations by n minus 1 only in case of sample, whereas in case of population I would go with the entire n minus 1. So that is one more concept that we need to be comfortable with when we are finding out the population variance and standard deviation versus the sample variance and the standard deviation. So in most of the cases, because we are talking about the deviation or standard deviation or variance as the dispersion in the mean, most of the times we see that anytime I present the data, I look at the arithmetic mean as well as the standard deviation being presented together only. Unless we have a time series data, in case of a time series data, I would even prefer the year on year growth kind of stuff. So I would prefer representing the geometric mean as well associated with the time series data. Now, the next thing which I would like to look at is other measures of dispersion which are slightly used in the investment world. I use words like semi-variance or semi-standard deviation. Again, another word that is used in the investment world, or probably a target variance or target standard deviation. So these are another forms of the variance and standard deviations that are used decently in the investment world. As we have already been talking about variance or standard deviation, they are the measures of risk of an investment, but they talk about both the upside movement as well as the downside movement, because all we have taken is x minus x bar squared or x minus mu whole squared. So even if the x is higher than x bar or x is lower than x bar, we are taking both of them as a measure of standard deviation and both of them as a measure of risk. But when I use the word risk as a word, I'm not bothered if I'm getting much higher return than expectation. If I get more than the expectation, it's not a risk for me. Only when I get lesser than the expectations, it becomes a risk. So that is where the focus is more on the downside only. Upside, why should I take it for the computation of the risk? So I am majorly bothered about the downside itself, and I want a measure that looks only at the downside of the mean. So that is where we talk about the semi-variance and the semi-standard deviation. So where the focus is only on the downside of the deviations compared to the mean, right? So what we do in computation, if here I have to take, the squared deviations, so I'll say downside squared deviations. I'll consider only those deviations. I'll take the square of those deviations where the return is lesser than that of the mean. So I'll put a simple rule saying if the return is lesser than the arithmetic mean, then only consider, or probably less than or equal to, I'll consider. If the mean is less than or equal to the arithmetic, if the return is less than or equal to arithmetic mean, then only consider the squared deviations. Otherwise, simply take it as 0. Don't consider it. Right? So, if I am going with that kind of a concept, I am taking the squared deviations only in some cases, whereas in some other cases it is going as 0. So if I'm taking the average of that particular number, if it is a semi, I mean samples, if I'm going with a sample, again the same logic, right? If I'm going with a sample, sum of downside squared deviations, first thing I'll find out. Sum of the downside squared deviations in this case is giving me something like this. So downside sample variance, if I am taking downside sample variance, I am doing this summation dividing by n minus 1 because it's for the sample. The downside semi variance, if I am taking this minus 1, telling me that the downside sample variance is that much and downside sample standard deviation is the square root of this, which is giving me around 5.68%. Only when I am considering the downside, my sample standard deviation has come out to 5.69% only. Right, when I am looking only at the downside, but when I looked at the overall sample standard deviation, it was 8.43%. So this is a way out where I can look at only the downside, right? I am not taking all the observations and I am not finding out the downs and I am not finding out the squared deviations of all the observations, only those observations which have fallen lesser than the mean. I have typically evaluated the standard deviation and the variance associated with them. So from this way, if I look at, if I am talking about a standard deviation, it looks as if the standard deviation, the regular standard deviation that we are considering, it is overstating the risk. Right, when I am looking at the regular standard deviation, it looks as if it is overstating the risk. The same way, instead of using the sample, instead of using the semi-variance or semi-standard deviation, which are again the measures with respect to mean, probably I can look at the measures with respect to target. Instead of looking at the measures with respect to mean, so I may define some target. There should be a minimum of 0% return. I have to be slightly more than 0 every time. So what I want is, what is the standard deviation of the observations that have gone negative only. I am not looking at with respect to mean. I am looking at the variance and standard deviation of the observations that have gone negative only. So what I can do is, again I will take only for the negative, I will take the squared deviations. So if my return is less than 0, that is where I will take the squared deviation, otherwise I will not. So my target, here I have set a target as 0. So when I am computing target based sum of squared deviations, I am getting the summation to be only this much. And from here, if I find out the target based sample variance, I am taking it as this number divided by n minus 1. The target based samples variance, I have taken the sum of the deviations divided by n minus 1. So this is what is my target based sample variance, and the target sample standard deviation can be found out by taking the square root of this, giving me that if I am going with a target based, probably my sample standard deviation is just 5.68. Here the target I have set as 0%. Whereas I can set a different form or different kind of a target altogether, and based on that I could see what is happening to my sample variance and sample standard deviation. So instead of directly taking it with respect to 0, I will take it with respect to I'll take it with respect to this particular value which I have set it as a target. So what could happen now if I say my target is a minimum of 1% monthly return? My target is minimum of 1% monthly return. What I could very well do is, here I could typically call it as target based squared deviations instead of saying negative. And when I apply it across my data, what I could see is the target based sample standard deviation is 5.69%. Now when I set my target, let's say at 5% per month, my target sample deviation is going to be 5.76%. So this is how, once I change the target, my sample standard deviations and sample variances can very well change. So that's one more. So basically what we can also see is, if my, see here earlier we have got the semi-variance, this is my semi-variance, whereas this is my sample variance full. What I am looking at is, if my return distribution is symmetric, if my returns are more or less symmetric, what I typically see is semi-variance might come out to be almost half to that of the variance. So the equivalence could very well be established. So probably here when I am looking at the semi-variance, variance divided by 2, the semi-variance is slightly, right, which says the semi-variance is the downward sample variance, which is nothing but the semi-variance. Probably let me call it as semi-variance and semi-standard deviation itself. So the downward, only the downward considered semi-variance is almost closer to half of the sample variance. If it is more or less equal to half, then it is like my return distribution are more or less symmetric. What we typically see is, though I am looking at semi-variance, semi-standard deviation, target variance, target standard deviation, they are slightly difficult to calculate. Though they have an intuitive logic, they are difficult to compute. But typically what we see is the variance and the standard deviation have a large number of applications in finance. When we talk about the Sharpe ratio, when we talk about beta, lot of finance related calculations, they use the sigma, which is the population variance or population standard deviations, quite effectively. All right. Now let's look at one more dimension that typically uses this measure of standard deviation quite effectively. Here I would like to bring in what is called as a Chebyshev's inequality. There is one good inequality that has been developed by Chebyshev, which uses the standard deviation, and based on the standard deviation he has given an inequality which says the proportion of observations. This talks about the proportion of observations within k standard deviations of the mean. He talks about the minimum proportion of the observations, the minimum proportion of observations within k standard deviations of the mean, irrespective of whatever is the data and the shape of the data. What he simply said is, at least 1 minus 1 by k square observations for k greater than 1, at least 1 minus 1 by k square observations will lie within k standard deviations of the mean. A very interesting result. If I am talking about 2 standard deviations from the mean, it means 1 minus 1 by 4, 3 by 4 which is around 75% of the observations. A minimum of 75% observation will lie between plus or minus 2 standard deviations of the mean. Similarly, when I am talking about the 3 standard deviations, 1 minus 1 by 9, 8 by 9, almost 88.88% of the observations will lie between plus or minus 3 standard deviations of the mean, irrespective of what is the shape of the data. Right? That's the generality that this theorem has actually brought out. Only at the max 11% of the observations can be outside the plus or minus 3 sigma limit. So it is going true for samples, population, discrete, continuous, any such kind of a data. But depending on an appropriate distribution, this can grow up. But minimum of these many, because the standard if the data is more, let's say, following a normal distribution, probably which we'll cover slightly in our later sessions. If the data is following a normal distribution, what is said is almost 95% of the observations lie between plus or minus 2 standard deviations. Almost 99.7% of the observations lie between plus or minus 3 standard deviations. But what Chebyshev has got out through his inequality is whatever, irrespective, even if I don't know what is the distribution, all I can say is a minimum of 75% of the observations will lie within 2 standard deviations of the mean. 89% of the data will lie within 3 standard deviations of the mean. That's an interesting point that comes out of the Chebyshev's inequality. Now, the other important point for us to understand in this context of deviations is a theory of coefficient of variation. Now, here we have measured the standard deviation, let's say for a sample or for a population. Let's say I have computed that this is the standard deviation. This is the standard deviation. Now, this standard deviation is an absolute. Probably there could be a possibility that if I am using a different data with a different mean, the standard deviation could be something else. Now, I should be able to compare the relative risk, because when I am saying the standard deviation, let's say I am talking about a data having a mean of 20 and a standard deviation of 10 versus a data having a mean of 100 and a standard deviation of 10, because standard deviation is an absolute measure. So, I may or may not be able to say that this is more risky than this or this is more risky than this, or I cannot even say that both of them are equally risky because the standard deviation is the same. Right? So, what I typically want is, if the data sets are there where the mean is extremely different or the units are completely different, if I want to compare the relative risk, which one of these two is more riskier? Which of these two is more riskier? When I want to look at more from a relative risk kind of a perspective, it's better that I go with a relative dispersion measure, not than absolute dispersion measure. And coefficient of variation is a one very good relative risk measure, because it does nothing but standard deviation divided by the mean, whether it is for a population or for a sample. So the standard deviation, in this case probably the standard deviation is 10 but the mean is 20, whereas here it is 10 by 100. So the coefficient of variance here is 0.5, here it is 0.1. So it is saying this is more riskier compared to this. The comparison becomes more easier, especially when the means are drastically different or where the units of measurement are very much different. So in our example back again, if I have to find the coefficient of variation, I'm simply taking the standard deviation divided by the mean. Standard deviation divided by the mean. One, it's a unitless quantity. So probably the standard deviation divided by the mean is giving me 5.61, and it is purely an unitless quantity. So it is completely talking about the risk per unit of mean return. Probably when I am talking about coefficient of variance, I can interpret it as risk per 1 unit of the mean return. That is how I present the coefficient of variation. And comparison of the dispersion across different kinds of data becomes more easier. And as I said, it's a completely scale free. Whether it is in, there is no centimeters or millimeters or whatever, because the standard deviation is expressed in the same units as the mean. So both the units get cancelled each other and it becomes a unitless quantity. So even if the units of measurement of two different data points are completely different, I can very well use the coefficient of variation as a measure of the risk per unit mean return. And one more dimension, especially from a finance perspective, what uses the standard deviation is a slight inverse form of coefficient of variance. Why I say inverse form of coefficient of variance is a Sharpe ratio typically is defined as the return. I'll just give the formula first. The excess return of the portfolio over the risk-free rate of return divided by the standard deviation. Now you look at it like this. Coefficient of variance we said as standard deviation divided by the mean. Probably look at it as 1 by coefficient of variance. We are talking about the mean return divided by the standard deviation. Or probably it is simply talking about the return per unit of risk. The return per unit of risk, correct? But what we typically talk of here is, in finance terms, we use a word called risk-free rate of return, which means even without taking any risk, I can generate a return called risk-free rate of return, which means without having a chance of losing even a penny, I can get within a year some minimum assured return of 6% or 7%. Typically, if you look at investment in government securities or investment in highly rated banks, there is no chance of losing money, but at the end of the year, I may get a 5%, 6%, 7% a return on my investment. So that kind of a return we typically call as risk-free, means even without taking any risk, I can get that much of a return. So whatever we are talking as return per unit of risk, we slightly change it as saying excess return per unit of risk, because RF is something that is assured. So whatever the additional I am looking at, it is the excess return per unit of risk. So that's where it's still an inverse of the coefficient of variance itself, but I'm taking the return, not just the return in its absolute sense, but I'm looking at it as excess return. So excess return per unit of risk is what I'm calling as the Sharpe ratio. And so that is where we use the word mean excess return kind of stuff. And typically what we see is this Sharpe ratio is one of the key tools in the portfolio's performance evaluation. Of course, we'll talk about a few other tools later, but portfolio's performance evaluation, I see that Sharpe ratio is one of the powerful measures because it is looking like if I am taking one additional unit of risk, what is that kind of a return that I am able to generate. So that's one of the prime reasons it becomes one of the mainstays as a part of the portfolio performance evaluation process. And in general, we are seeing that as the Sharpe ratio increases, the excess return per one unit of risk is typically increasing. But what could typically happen is, if the return is negative, if the return on a particular portfolio is negative, it gives me a negative Sharpe ratio, which is very difficult to interpret. So in those cases, I may not rely on Sharpe ratio, especially when it comes out to be a negative value. But the expectation is, if I am taking the data over a long term, the more I am taking the risk, I should be compensated with the return for it. Probably for a short term periods, this ratio could be negative, but when I am looking at a longer and longer term, this value should be positive, because if I am taking more risk, unless I am compensated with more return, there is no reason why I would go ahead with that kind of an investment. So negative Sharpe ratios need to be looked at more critically. And one more comment that goes with respect to Sharpe ratio is, it is taking only one unit of measurement, only one aspect of the risk, which is the standard deviation. And as we have already looked at, standard deviation is a very good measure, or is an appropriate measure, only when I talk about my return, my distribution being more or less symmetrical, because it takes both the upside as well as downside. If it is more and more symmetrical, probably standard deviation is more or less a decent measure. But if my return distributions are completely asymmetric, right, probably so many small gains but very few large losses, where the standard deviation may not come out to be a decent measure at all. So in those cases, the Sharpe ratio will have a decent limitation in terms of interpretation. So probably as we move along, we'll try to see what we can do to address those kind of distributions and those kind of data. But here our intention is to understand how the deviations and dispersions could be calculated, and how well they can be used in the world of finance and investments to understand the characteristics of the return data, and to assess the performance of my various investments. All right. Now that we have understood the definitions of, or the usages of, the central tendency as well as the dispersion, now we turn our attention to the another dimension of measuring the characteristic of the data, which is the skewness, which broadly talks about the symmetric nature of the data. Because many of the times what we see is just the mean and the variance may not be sufficient to describe the entire distribution, right? The reason being, if I am looking at the variance, we have taken the observations, the subtracted the mean and squared. So the positives and negatives, all of them are getting translated into positive. But all I want to know here is, whatever are the large deviations that I had, are they really positive or negative? So what is happening with the large deviations? A square is not telling me anything about where the deviations are more. Is it more towards the left side or is it more towards the right side? So I need a few more important calculations to understand the data in a much more effective manner. Probably if my data has been more symmetric, I would not have bothered too much, because the positive deviations will be more or less similar to that of a negative deviation. But if it is not symmetric, that mirror image cannot be present. So some kind of deviations will be much more towards the positive side versus lesser compared to the negative side, or vice versa. Only when the distribution is more normal. One of the examples of symmetric distribution, when I plot the frequency distribution in the form of, let's say, histogram or a polygon, what I typically see is, if the shape of the histogram comes more like this, I call these kind of distributions which look like a bell shape, more symmetric. This kind of distributions typically are called as normal distributions. In these kind of distributions, probably I don't need to bother too much about the deviations more towards the negative side or towards the positive side, because they are more or less uniform on both the sides. So these kind of distributions being called as normal, they are used very heavily in the world of finance, right? As we move into the financial concepts, we'll try to understand all those things, but especially in the portfolio selection process, are probably used in heavily in the risk management. Various departments, various financial applications use the concept of normal. Some of the important things associated with the normal distribution, the mean is same as that of the median, and only the mean and the variance are sufficient to describe the distribution. I don't need to understand whether the deviation is more towards the left side or towards the right side, because it's already symmetrical. So only these two are sufficient. And few more interesting aspects is what we typically see, just linking it with the Chebyshev's inequality which we discussed earlier. A more improvement over the Chebyshev's inequality is, roughly we find around 68% of the observations in plus or minus 1 standard deviations of the mean, 95% of the observations in plus or minus 2 standard deviations of the mean, and much more than 99, close to 99.7% of the observation in plus or minus 3 standard deviations of the mean. So some of the interesting things that can be brought out, if at all I can see that my data is more normally distributed, or but if it is more non-symmetrical, then I say that that particular distribution is skewed. So that skewness could be either a positive skew or a negative skew. So when I try to plot a histogram, if I get a plot more like this, or sometimes I may get a plot more like this. So if I am getting a plot more like this, what we say is this is called as a positively skewed distribution, whereas this is called as a negatively skewed distribution. What does it mean? If I look at this, the frequency is very high for the smaller values, but for very large, there are some very large values for which the frequency is much smaller, right? Because this is a frequency distribution curve. So we can very well say that there are frequent small losses, more frequent but small losses, whereas less frequent extreme gains. Whereas here I am seeing very less frequent extreme losses, less frequent extreme losses, because left side is like a loss, and probably more frequent small gains. So this is called as a negatively skewed kind of a distribution. So we see that the tail is high on the right for this, whereas the tail is very much higher on the left. And typically the peak, if I am considering it as the mode, in case there is a mode for this distribution, probably if I consider this as the mode, here what we say is the mean is somewhere here and the median will be somewhere in between. So probably it can very well be said, if the data is positively skewed, I will observe that the mean is greater than the median, which is greater than the mode. But if I am seeing that it is a negatively skewed, I could see that the mean is less than the median, which will be lesser than the mode. So in our data, what is happening? Just look at your data. What was the mean? Our mean was 1.5% and median was 1.3. So mean is greater than the median. So probably I should see that it is a positively skewed kind of a distribution. So just by observing the relationship between the mean and the median, I could see that it could be a slightly positively skewed because mean is slightly above the mean. But wherever I am seeing a big difference, I see a skewness also could be decently higher. So generally a positive skew is more towards limited downside. Downside is very much limited because it cannot go until here. The downside is pretty much limited, but I can have a very few upside. So generally investors are recommended to some extent of positively skewed distribution because one side they are protected on the downside, the loss cannot go beyond a certain point, very rare going of a loss beyond a certain point, but on the other side there could be a few occasions where the profits can go to a very large extent. So that is from that reason we can directly go ahead with slightly positively skewed kind of distributions also. And the way we compute the typical skewness is each observation I subtract the mean if I am going with a sample, but this time we do the cubed deviation. When I did the square we called it as variance, but now I am going more with the cubed deviations. So this minus this cube, I add all these deviations. Just to normalize it, I divide it by the standard deviation cube. I divide it by the standard deviation cube to make it more error free, to make it more unit free. So again the units don't exist for this coefficient of skewness. The units don't exist, and of course here I have to take the average of the cubed deviations from the mean divided by the standard deviation cube. But to be more precise, instead of n, the actual formula says this multiplied by n divided by n minus 1 into n minus 2. This is the real formula, but what happens is as n tends larger and larger, as n becomes larger, what we see is this entire thing gets reduced to 1 by n. Right, as n tends to larger and larger, this entire thing becomes equal to 1 by n, more similar to 1 by n. That is where we talk about the coefficient of skewness can very well be measured as average of the cubed deviation from the mean standard divided by the standard deviation cube. So if it is a symmetric distribution, I'll see that the skewness is 0. If it is a positively skewed, I'll see that the skewness is positive, and if it is a negatively skewed distribution, I see that the skewness will be negative. So whenever I am seeing that the skewness is positive, because mean is greater than the median. So mean is greater than the median, which means more than half, right? More than half of the, or 50% of the observations are lesser than the mean, because median is the one that divides the data into two. So median is towards the left of the mean, so which means more than 50% of the observations are less than the mean, and only less than 50% of the observations are above the mean, right? Or similarly, in case of a negative skew, the opposite can very well be visualized. So if at all I have to compute the coefficient of skewness, right, in my data, if I have to compute the coefficient of skewness, probably let me take the cube deviations to understand the concept first, then I can apply the formula as well. I'll take cubed deviations from the mean. So I have already computed the deviations earlier, so just I'll take the cube of those deviations. These are the cube deviations from the mean. Either I can simply take the average of these cubed deviations, right? Probably I'll because the number is anyhow n is very large, average of the cube deviations, if I am taking, it is coming out to something like this, the average of the cubed deviations. So if I want to find out the coefficient of skewness, I can very well do the average of the cube deviations from the mean divided by the standard deviation cube, the cube of the standard deviation. So this is giving me that the coefficient of skewness computed through this is around 0.53. But if I directly find it, there is an Excel based formula for finding out the skewness. So if I take the skewness of the returns data directly, probably I am getting again 0.54, because it would have computed using instead of using average, it could have taken n divided by n minus 1 into n minus 2. So that would have been probably just to understand, instead of n, if I go with n divided by n minus 1 into n minus 2, I may get a slightly higher value, and that is what has resulted in the coefficient of skewness. So either of the ways, as n is becoming more larger, I can just approximate it to average of the cube deviations divided by the standard deviation cube. So that's one more thing that I can look at with respect to the skewness. So as I said, from an investment perspective, positive skewness is still a slightly preferred one compared to choosing a one with negative skewness in the data, right? All right. Now, one more dimension that I would like to look at in a data, understanding the pattern of it, is the kurtosis, wherein another way I am trying to look at the data differing more from a normal distribution. We have said a normal distribution is something which is symmetric on both sides, and probably there is a kind of a gradual fall looking like a bell. Whereas in case there could be another scenario where I am looking at the returns, or I am looking at the values more clustered around the mean, more clustered around the mean, and more extreme, as well as more in the tail, more in the extremes. So typically we talk about, when I look at their frequency histogram, it would be more peaked than normal, and at the same time it has fat tail. The tails are much more fatter compared to the normal. Or it could be less peaked than the normal, and along with that having thin tail than the normal. So these are measured through a mechanism called kurtosis. Kurtosis again is going with the deviations, but this time it takes the fourth power of the deviations, the average of the fourth power of the deviations divided by the standard deviation to the power of 4. So again the intention here is looking at the percentage of smaller deviations from the mean and percentage of extremely large. So I am looking at smaller deviations from the mean as well as extremely large deviations from the mean, not somewhere in the middle. Extremely small deviations, extremely large deviations. What we see is some distributions can have very high on both these counts. Some of them can have very low on both these counts. So whenever they are having very high, greater proportion of very small deviations from the mean and as well as greater proportions of very large deviations from the mean, they are called as leptokurtic distributions. Whereas if I am having a very few number of smaller deviations as well as very few number of extremely large deviations, we call them as platykurtic distributions. And if they are having more or less equal to normal, moderate number of smaller deviations as well as extremely large deviations, we call those kind of distributions as mesokurtic, wherein normal distribution falls in that particular category. So whenever we are seeing this kind of a category where the large number of deviations are there from the extremely large deviations from the mean are very high in number, probably that kind of an investment is more of a risky investment, because there are a good possibilities of getting extremely high losses, right? So whenever we are talking about large deviations, large surprises, this is bringing me the situation of leptokurtic kind of distribution. So basically it's like when I look at a graphical representation, let's say if this represents a normal, what we typically see is the tail will be higher, but at the same time the peak will be like this, and again the tail will be higher. So these kind of distributions go as leptokurtic, whereas the tail will be lower as well as the peak will be lower when I am looking at platykurtic kind of distributions. And the way we compute, as we have already said, I take the fourth power, right? Fourth power of deviations. So the same deviation, deviations, I take the fourth power of them. So these become the fourth power of the deviations. I'll take the average of the fourth power, average of fourth power deviations. So I'll get the average of the fourth power of this, and if I want to find out the kurtosis, it comes out as the average of the fourth power divided by the standard deviation to the power 4, which is working out as 5.38. So that's what comes out as the kurtosis. Again, here also, instead of just taking the average, people look at it primarily like people look at it as xi minus x bar to the power 4 divided by s power 4. Instead of just taking 1 by n, they look at the actual formula goes as n into n plus 1 divided by n minus 1 into n minus 2 into n minus 3. But again, as n gets larger and larger, we see that this entire thing works out to 1 by n. That's the reason we get the excess kurtosis, we get the kurtosis as the average of the fourth power of the deviations divided by the standard deviation to the power 4. And what we typically see is, if the distribution is normal, we see this kurtosis value will be equal to 3. So if it is greater than 3, we call it as leptokurtic. Equal to 3, we call it as mesokurtic. Less than 3, we call it as platykurtic. But just to make sure that, linking it in line with that of a skewness, what they have come out with is they have designed a new term called excess kurtosis. Excess kurtosis typically comes out as kurtosis minus 3. Simple definition. So basically it means for a normal distribution, the excess kurtosis will become 0 directly. So anything positive excess kurtosis we call leptokurtic. 0 excess kurtosis we call as mesokurtic, and negative excess kurtosis we call it as the platykurtic kind of distribution. So what Excel as a formula directly gives as a kurtosis, where I use the kurt as a formula. Because of small approximations, our value will be slightly closer to that. So what Excel gives is the excess kurtosis, not the kurtosis. So after the subtraction of 3, whatever the kurtosis is coming, that is what is being presented by Excel formula called kurt. So in general, when I am just working with samples of, let's say, 100 or above, what we typically see is a skewness which is more than plus or minus 0.5 is very severe, unusually large. Similarly here, when I am seeing that the kurtosis is greater than 1, then I can see that it is extremely large, which means there is a very large leptokurtic behavior that is being presented by the data. So it's a very large fat tail. There are some extremely large outcomes that are coming in the data. So there could be a very good outcomes, very bad outcomes, but they are very extreme outcomes. So that's one thing that can come out by the understanding of the skewness and kurtosis and all these 4 dimensions. So typically people focus on central tendency, the dispersion, the skewness or the symmetric nature of the data, and the peakedness as well as the tails. So these 4 dimensions of a data describe the data in full, and that is what will become an important aspect of any kind of analysis for us. Different kinds of mapping to different kinds of probability distributions can be done once we have a decent understanding of these 4 different dimensions of the data. Alright. Now just one point that was missed out as a relationship between the geometric mean and the arithmetic mean in the investment context. Whenever I have to report past performance over the last few years, geometric mean is much more appropriate. But when I am looking at expected kind of or forward looking kind of a performances, when I have to look at expected performance in the future, it is advised that arithmetic mean is much more appropriate compared to a geometric mean. And just as one more dimension, just to quickly find out, though we have said geometric mean is always less than or equal to arithmetic mean, equality exists when all the values are same. There is an approximation relationship that came out in terms of finding the geometric mean, which says the geometric mean is generally equal to arithmetic mean minus the variance by 2, half the variance. So arithmetic mean is lesser than the geometric mean, arithmetic mean is higher than the geometric mean by half the variance of it. If I have to go back with the data, the geometric mean in terms of arithmetic mean, if I am looking at, it should be the arithmetic mean, again this is an approximation formula, arithmetic mean minus the variance divided by 2. So if this is the variance, variance divided by 2. So overall here, if I am looking at the geometric mean, right, I am looking at the variance by 2. So my geometric mean should come out as 1.15%, which even using the formulas, we got it somewhere around 1.16%. So there is a small approximation in the usage of geometric mean in relationship with the arithmetic mean and the variance, right? So these are some of the basic statistical concepts along with the market returns, which I wanted to cover as a part of your understanding of the basic statistics for various finance related applications. If you have any further queries regarding the same, you can very well get back to me by giving me the call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.